Hi everyone. So I'm Yiming. I'm a postdoc here. So this research is mainly conducted by the PI, which is Professor Opabola, but unfortunately he cannot be here, so he left the mic to me. So if you have any question after the talk, feel free to send an email to him. So he absolutely loves to say some surprise research question in his inbox. Okay, so the reason we want to conduct this research is that we noticed that due to the rapid urbanization in 1960 to 70, so there is a lot of bridge constructed, and most of them are deteriorating and exceeding their design service life. So here is a figure from the ACI report. They just released this morning. You can see the concrete cover just fall off, and the rebar becomes corroded. So that will definitely affect the service life. And we also noticed that several modern bridges are deteriorating at an undesirable rate. Also, considered due to the climate change, such as global warming, sea level rise, and CO2 emission change or relative humidity, all of them can accelerate the corrosion and in turn to shorten the lifespan of the US bridges. And also, there is a significant funding gaps, is more than 300 billion over the next 10 years to bring the national bridge into the shape of a good repair. So therefore, we need efficient procedures to predict the residual service life of the bridge and the climate change, and also identify the most vulnerable bridge which needs the intervention urgently. So in this way, we can provide the information to stakeholders to use the limited funding or limited budget more effectively. So there is a state-of-the-art report from the ACI. They try to predict the service life, but there are still some research gaps need to be addressed. First, the climate change impact on corrosion initialization and propagation in the bridge are not quantified. And also, there are multiple interconnected corrosion mechanisms that haven't been properly integrated. And also, there is an urgent need for the dynamic risk assessment on the service life prediction, especially for the bridge susceptible for extreme loading. So here's a little bit of background. We start from the classic PBE framework, which is the triple integration, considers the hazard structure loss and damage and loss analysis. And maybe 10 years ago, there is an updated version of the framework, which is the dynamic PBE framework, consider the time-dependent hazard. So using this logic, so we try to treat the climate scenario as another dimension, include one more integration on the climate scenario. In this way, we can incorporate the climate scenario in the in the PBE framework. Here's our methodology. We start from the climate change scenario, and then we perform the hazard analysis. This hazard analysis could be time dependent and also could be the climate dependent. And then we design the bridge and go to the corrosion analysis. So basically, we analyze the corrosion initialization and propagation and link them to the building capacity deterioration. After that, we perform the structure and damage analysis, and we can get the hazard curve and the fragility curve at each year, which are the time dependent and also could be the climate change dependent. And after integrating these two curves, we can get the curve to predict the service life. With all this information, so the stakeholder can make the decision making in terms of the bridge inspection, repair, or replacement. So starting from the incorporating climate change scenario, we combine multiple climate model and climate scenario using a logic tree. Here is one example. We can consider assign the different weight for each model and scenario. And then for the corrosion will be initiated, which is the time from the construction until the onset of active corrosion at the steel surface. So basically, these models are the function of the temperature and relative humidity, which allow us to link with the climate change. And also consider there are several corrosion initialization models, so we also use a logical tree to combine them. Then we go to the propagation stage. In this stage, with the increase of corrosion level, so the structural capacity will drop. And in this case, we mainly consider the pitting corrosion, and the uniform corrosion will be studied later. After we have the corrosion and we know the corresponding mass loss in the reinforcement, and then we can link to the capacity deterioration. So we're starting from the material level. We know the reduction in the reinforcement cross section, and then we know the corresponding the reduction in the strength, and consider the concrete cover will crack. So we can quantify the degradation of concrete rebar bonds. After we quantify all the material level deterioration, we can go to the component level, which means we can estimate the deformation capacity and effective stiffness. And here is a backbone comparison. The red one is for the corroded columns. And then we can get the relationship between the mass loss in transverse rebar and longitudinal rebar with a reduction in deformation capacity. After that, we can predict the inspection time and the residual service life. In this case, we model the time of the initialization as a probability distribution. So with a given threshold, we can trigger the time to do the detailed inspection. So using the similar logic here, so we can model the probability of mass loss as a distribution and also define a threshold to trigger the time to do the repair. Eventually, we will go to the replacement stage. Basically, we have the hazard curve and the fragility curve. After we integrate them, we got the collapse rate versus time, also with a given threshold. Yeah, we can get the time to do the replacement, which can also help us to determine the residual service life. For our case study, we focus on the reinforcement concrete bridge, and we try to design them for 3 fundamental periods and consider the 3 exposure classes, which are defined based on their distance to the salt water. And here's our results in terms of the chloride concentration on the surface of transverse reinforcement. So as you can see, for the red lines, which are the buildings which are the bridges in the splash area, we get the highest chloride concentration. And in this case, we also consider using the logic tree to quantify the uncertainties. Here are the results for the longitudinal rebar. After we have the chloride concentration, we link them to the mass loss. So this is our result for the mass loss in transverse reinforcement, and this is the mass loss in the longitudinal reinforcement. Then we define a nonlinear model. Here we try to, for simplicity, we use a single degree of freedom to represent the reinforcement concrete bridge. And we can model their deformation capacity based on using the hinge with IMK material. And this material is also calibrated with some experiment data. So after that, we go to the surrogate model development. In this case, we use cloud analysis we're using cloud analysis to define the relationship between the mass loss in the rebar with collapse fragility. We get this heat map. And then we go to the dynamic risk analysis. For this case study, we assume the hazard is stationary because we try to isolate the climate change impact on the bridge. So as you can see, the fragility curve will drop from the 2000 to 2100 due to the corrosion. And after we integrate these 2 curves, we can get the service life. For example, if we define the collapse rate as 1% in 50 years, as you can see for the black lines, which are the corrosion without climate change, this bridge could survive to 2100. But if we consider the climate change, it will only up to the 2092. But if we consider more conservatively, which we use the upper bound of our uncertainty study analysis, it will up to the 2055. So with this methodology, we can evaluate we can perform the dynamic risk assessment for individual building. And our ongoing study is for the network scale. So we start from the transport network, there are maybe few bridges connect with several communities, and we collect the building inventory information, and we perform our dynamic system level assessment of individual bridge, which is what I described before. And then we go to the output. So we can get the inspection time and cost, and the time-dependent collapse risk, and the direct and indirect cost, and also the repair time and cost. The results I shown before are mainly about the time, but we can do the similar thing to estimate the corresponding cost. After we have this output, we go to the network analysis. So in this analysis, we consider at the network scale. So we can have a few assessment and management scenario, which based on how much you want to spend on the bridge maintenance for this network. So we can get the corresponding the functionality loss risk and the maintenance cost. We can make them climate change dependent, which is they will be very with respect to time. So here is one very basic example here. We define the performance objective as the network remain functional if every community remain reachable from each other community. And then we analyze each building's collapse rate versus time. After that, we can aggregate them together at the network scale. As you can see, for the for the yellow lines, which is the line we consider the corrosion, but there's no climate change and no maintenance. So the functionality loss risk will increase with respect to time. So if we consider climate change but no maintenance, which is the red lines, this risk will increase significantly. But if we consider there is a maintenance, so at some point when the repair or replacement is triggered, so the risk could drop. So you can see this is shown as the blue lines. So it's very similar to the one without corrosion. So here are the corresponding maintenance costs. In these case studies, actually only the blue lines, which is the corrosion with climate change and maintenance, only this one we consider the maintenance. So you can see the maintenance costs drastically increase. So this is a very basic example, but we will maybe consider more realistic case in the future. Then go to the summary and the future work. So in this study, currently we develop a framework for the dynamic risk assessment and service life prediction. And we successfully applied this framework for a reinforcement concrete bridge. And based on our case study, it shows that climate change can reduce the service life by 8 to 45%. And also this framework has been applied at the network scale to evaluate the risk of functionality loss and the maintenance cost of the transport network. But there are still a lot of things we can do in terms of the future work. First is at a system level, we can integrate the framework to account for the combined effect of chloride ingress and carbonation-induced corrosion, which means we can refine or improve our corrosion model. And at the network scale, we plan to apply this framework to a real-world test bed. So this will allow us to do some calibration and fine-tuning of our framework. Okay, thank you. Thank you for your attention.
Thank you. Are there any questions?